We have mostly Zoom participants, right?
Probably.
Okay.
So go to the link.
So I'll make you both co-hosts so you can command Zoom.
Okay, the passcode.
Is Lisa?
Alright.
Should be the same, but just in case.
Yeah.
Lisa SD working.
Recording in progress.
Yeah, so I mute you because the hour will be your microphone. And
This is the Emory session.
Mhm.
Yes.
Mouse.
It will be.
Yeah, so Chris, actually, you know how everything works.
Yeah. Do you want me to sort of share it or?
No, just I'll also make you co-host so then you can
Oh,
be
I guess there's a power strip.
in charge if anything happens, and I'll be in the next room.
Let me find.
Yeah, I was thinking. Did it just this one to charge the computer? Yeah, also because there are no plugs.
Technically, mine is charged. You
No, don't worry. We survive it. Look for solutions.
So that there are plugs
Where?
on the pedestal
Your mic's not on, right?
down here.
I think.
Okay, but it's
Yeah, it's
No, I
not
think
ideal.
it's just maybe the
Depending
audio
how
from
long,
the
depending how
laptop.
long the cable is.
What? Yeah.
No, yeah, that's too long.
Let me just put it down.
Where's the Zoom link? Sorry, I'm struggling. Yeah, and it's not working for me. Ah, here we go. So. This one?
Shall we start? Do people on Zoom hear? Oh my God, this is still. Okay.
Speakers,
Do you
microphone.
hear me?
Yep.
They do. Okay.
Yep, they hear you.
Okay. Good. So I think I would like to start by asking everyone in the room and in the Zoom room any comments or you know, any remark about what we tried to explain today about the ideas of Project 3 and the fact that there are two options that at the moment they seem equally liked by the people who went on voting. So we still have a tie for the options 1 and 2. And as I said yesterday, it doesn't mean that we have to do forcefully only one, but it would be also good to hear your comments and you know, in one or the other direction. Or even more general questions about the whole idea and how we should go about it. And so who wants to start?
Do we have an agenda or is it just?
It's very, no, I mean, I didn't prepare an agenda because I first wanted to have a feeling of how people see this, you know, whether they have some remarks compared to what I showed today, you know, the idea of focusing on torques and orbital decay, which is the same, in that sense, is same with both option 1 and option 2.
So I don't think I had to run out through some of this morning
Yeah.
session, so I'm not sure. The goal of this is to produce something for the Red Book. Is this?
I don't, well, okay, this is very ambitious.
Okay.
So I think the catalogs are probably more in line with producing something for the Red Book because they will use material that is already existing. At least the idea, for example, of Project 2 is to use material, you know, published simulations and then put them together to compare the catalog that you get from them. In our case, we have to essentially run new simulations to compare them because we have to start with, you know, the same or as close as possible setup and, you know, control the parameters. So we have to do some new work, some new simulations. So it will take time, even if we shoot for something very focused and, you know, we will have a very basic analysis. I don't think it will take less than a year and a half to have something that we really understand, in my experience with previous similar work. So I think it might have an effect later, but I don't think we can produce something that is immediately useful for the Red Book. But certainly if we already see some trends, maybe at least, you know, we are more confident about some stuff that will go into the Red Book, for example. But I wouldn't see directly related to it.
There's a hand up.
Oh yeah,
on Zoom.
Alessia.
Yeah, hi, hello. So yeah, I was just wondering whether these, so I'm referring to the sub-parsec project, just because it's the one I'm mostly interested in. And I was wondering, like, how are we planning on doing it? I mean, does it differ from the KITP code comparison project? Because I think that since we want to focus on massive black hole binaries, then probably we want to compare a much more physical model compared to like instead of like running, I don't know, isothermal, very idealized scale-free simulations.
So yeah, let me clarify the relation with the KTP project. If you remember, the difference that we have in mind is that we are going to look at very unequal mass binaries into the IMRI regime, if you want. So that is very different from what is being done at the moment, at least as far as I know. What is being done at the moment, you can actually say more because you are deeply involved in that. For the KTP code comparison is primarily focused on equal mass binaries or similarly mass binaries where you have, of course, a circumbinary disk, whereas in this case, we will not have a circumbinary disk. We would evolve a setup that is more like what you would do in planet migration. So you have a small perturber, a small black hole, evolving around a much bigger one. So you have a smooth accretion disk. And that's basically the setup that we were thinking of using, which is complementary to what the KTP project is going to produce. I don't mean, do you agree with this?
Yeah, no, I totally agree. Yeah, sorry if I lost this part on the mass ratio.
The type of thing that conversation I wanted to have at the beginning, make sure that people agree, and then that there are no dubious points in going ahead with this.
Yeah, no, I was just worried about the I would say the equation of state that we want to use, since it has been found in the literature that especially in the planet regime, sorry, the having an isothermal or a radiative disk makes a big difference in terms of torques.
Yeah, you are completely right. I think we have to eventually go into something like simple radiative cooling model, but I think to start with, to align the codes, we need to start very simple, right? In the code comparisons, usually if you don't start very simple, it's very hard then to align the codes. And then when you add more complicated stuff, it's difficult to do the comparisons. So I would start personally with something like isothermal or adiabatic, or maybe both. We probably have to do both, adiabatic and isothermal. And then if we see that very quickly we can align the participating codes, meaning get comparable results on this very basic setup, then we can move, as soon as we can move to a model where we have some implementation of cooling, something simple like a beta cooling model, or a relaxation cooling model, something that is very easy to code if people don't have it already. But I would start with something simple like isothermal and adiabatic to make the first alignment of the code results.
Okay, makes sense to me.
And then actually, because you mentioned the KPP code comparison, I have been emailing some of the people involved in that, especially I've been emailing with Dan Dorazio about this. I mean, Dan couldn't be here today because he's sick. Otherwise, he would have connected on Zoom. But we have, kind of updated ourselves on what was going to be discussed. And, he told me that, of course, if we go ahead with this, and we would definitely have an interaction with the other group. So, it would be he and probably also Paul, who is probably leading the effort, would be happy to connect with this other code comparison frequently, so that we do things that maybe even in the structure we could do something very similar. Start with a similar approach in how to do the analysis, for example. But you Alessia, are still working in the code comparison, right?
Yeah. We're just waiting for Paul Duffel to, sum up all the stuff that we uploaded.
You have already done. I mean, you have already many codes that have produced.
Yeah.
Results.
Yeah. No, we are. We have a lot of data now.
So, for example, one thing that I was chatting with Dan about was to start with the same group of codes, possibly.
Mm-hmm.
That would be because then to have interaction between the two projects. So that would be already a point of contact to have the same set of codes.
Yeah.
Of course, here I'm talking in the case of option 1. Option 2 is a bit different because it needs self-gravity, and not all the codes have self-gravity, or not all of them have efficient self-gravity. But for option 1, we don't need that, so that's also easier. When any comment, I see that Alessandro is also online. Do you have any comments also on option 1 and option 2 as to alternatives?
Well, not exactly. I think the point in general would be to see, well, also according to the number of people that I see here, I don't know how many are not attending but are interested into this comparison, but we should see how many people are willing to work
absolutely.
one or the other, because if there are only 2 people for the larger scale one, probably it's better if we focus on the small scale one. I'm working with Alessia on the circumbinary disks, so I'm working more or less on both of these scales. So I think this is something we should keep in mind, because we would like to avoid having a code comparison with 3 people involved, and then we have to look for students or.
So this is something that we surely have to avoid. At the moment, we have a tie. I think it's like 15. The people who voted are 15 for option 1 and 15 for option 2. I think some people voted both, although we repeated not to do it, but I guess maybe they just are interested in both. But anyway, so it's not a large group, but if at least we have 15 people that are interested and are really committing, that would be a good enough starting point.
Yeah, I agree. Yeah, and it's very likely that among these 15 people, the number of codes involved would be
It's less,
larger.
for sure.
So
Yeah, in fact, no, I agree. And in fact, I was thinking to reach out more actively. You know, if there is an initial seed group that is, you know, very keen on doing this with, let's say, at least 3 or 4 different codes, then we can reach out actively. I can reach out actively to other people in the working group, but even outside the working group. It doesn't have to be just inside the working group. You know, if it's really a matter of attracting another code that would add a lot to the comparison, we can even reach out outside the working group.
yeah. The only comment, but well, we are both in the Agora, so we know how it works, is to keep things short, not to spend too much time, because with Agora, as you also said yesterday during the talk, well, it started in 2012 and now it's moving so slowly that people moved from one institution to the other, started working on different things, and the interest was lost in some sense. So I think in this case, we should try to keep focus. And I think, well, but maybe Alessia can confirm, with the KITP code comparison, I think things are working properly. When I was there, I insisted with Paul and then to have something on a short time scale so that people can focus on that and then move on, but at least we would have something out.
Yeah, no, I completely agree. The Agora from that point of view is not a good model. It's a good model in the sense of many codes were involved and are involved, but not in overly ambitious plans that, you know, as you said, you know, they came out in the end inefficient. But yeah, the KTP code comparison seems to be on the right track. And the other one that I mentioned yesterday on the planet migration that was published a couple of years ago also was quite fast, because it really took less than 2 years from inception to publication. And, and the reason is because it was very, very contained. You know, just look at the migration under a different set of initial conditions and publish it. That was, you know, looking at the migration rate, and that's it. There was no other analysis done except that, and whatever was useful for that. Yeah. So I mean, here we could do the same thing. Maybe we can add a little.
Yes. I think in this respect, probably the larger scale simulations, the one on circumnuclear disks, because of the physics involved, the subgrid physics, it might take a longer time.
Yeah.
Because this is one of the problems of the Agora as well, that if you want to keep under control the subgrid physics and have something that is consistent among different codes, then it will take time for people to run and check and maybe vary some parameters. Probably the small scale, the IMRI scale simulations will be easier because the subgrid physics is more limited in this.
I completely agree. Yeah, so in that, you know, we could really, you know, the level of difficulty that we could add is adding cooling, for example, as Alessia was suggesting, but we don't need to add any subgrid physics. The only thing that might be not so trivial, again, given what we saw in the planet migration case, is if you add sync particles, like some published papers already have done, right? Adding sync particles to do accretion, that is very delicate, because each code will do it in a slightly different way. The boundary condition can affect the accretion a lot more than what usually people expect, and then they affect the migration as a feedback effect. So that the sync part is, at least what we found in this Fletcher et al. Work, was really the more tricky thing to align. In fact, we didn't align in the end because there are some differences in the codes you cannot eliminate. And in fact, this was also what produced less convergence. But I mean, this is something we will find out if it's really.
No, I agree. I think we should try to agree on what we want to include one or both projects in any way, because as you said, the sync implementation can be tricky for some codes, or well, might take some effort, and in other code is already there. The same is valid, for instance, for radiative cooling or star formation. We have to decide what we want to include and up to which point.
Yeah, a first set of runs could be done really in a kind of vanilla.
No, exactly.
Where you do basically just a point mass evolving in the disk. What we have to decide if we want to move the perturber or keep the orbit fixed and measure the torques, because that's also something that differs among different codes. You know, the default is not the same for different codes. In that.
Yeah, also for the circumnuclear disk, for instance, we could start with the simplest cases, and then depending on the amount of time needed for the inclusion of different subgrid prescriptions, stop at one point, at one stage, and say, okay, this is what we have, and we can publish something in order to avoid the delays that we saw in Akura.
So in that one, you started out. So remind me, do you actually move the secondary black hole, or do you keep the orbit fixed in the default setup?
But for what? For circumnuclear disks or?
Binary disk in the KTP.
For the circumbinaries, well, the simulations Alessia performed are live simulations with the binary that evolves. For the code comparison, now she has run simulations with the binary fixed, because that was what the group agreed upon. But the published simulations are with the live binary.
Yes, but for the code comparison, the default is
fixed.
Yes. So if I may add to that, the problem with changing the mass ratio is that if in the type 2 migration like regime, then fixing or not fixing the binary orbit might have a huge impact on the torques. Like mostly because if you change the planet mass, then you either open or close the gap.
Yes, I agree. In fact, but I guess you also in the KTP code comparison, are you planning also to have a second set of runs with the live secondary, or? I
don't think so. I don't think Paul wants it.
I think, for this one, I would like to, I mean, that's my opinion, of course, then we have to agree on this among the people who will do it, but I would definitely like to have the live case, maybe not the first thing that we do, but eventually the live case should be the goal. But yeah, so we could start with something that I'm just taking notes now, then I can share them. I just open a Google Doc to put some notes of what we are discussing. So I think the possible basic setup could be something where we have fixed orbit for option 1, of course, a fixed orbit secondary, circular orbit, of course, that would be the starting point, and then we might have isothermal and adiabatic, and initially just a softened point mass without the sink. This is what I would do. This is a bit what we did in Fleischer et al. We started out with no sink.
Yeah, I think probably as a subsequent steps before thinking about sync particles, probably having a live binary might be the most important thing, because Paul said that, well, in the code comparison, KTP code comparison, he didn't want the live binary because I think in Disco they found it hard to have an accurate evolution of the binary of point-like particles, and so they prefer to avoid it. But I think this is an important thing. Well, so
there's a comment on this.
No, I would disagree with the reason because I know Paul.
Yeah.
oh, okay.
I think it depends on what question you are trying to answer, whether or not you need a live binary or not. So I think, Paul's opinion is usually that making a live binary just makes the simulation expensive and it doesn't add so much more information. depending on what you're trying to answer. I mean, he's done the work where you artificially move the binary, so you kind of can see how torques change with the migration. And that gives you information, and it's much, much cheaper. So, again, yeah, I guess it just depends on what are you trying to answer. Measure what torques are at earlier stages, or are you interested in already gravitational wave emission, for example?
I don't get why the simulation should be more expensive when you evolve the binary. It's two particles that dominate the potential. If you say moving from 2D to 3D, I completely agree, because with Alessio as well, with 3D, in order to have a similar resolution, the simulation becomes much more expensive. But adding two particles, I'm not sure it's so expensive. Also because, as you said, Paul evolved the eccentricity of the binary in the simulation analytically. And in the end, to do that, you have to write two equations in addition to the evolution on your code. I think the point is to keep the evolution of the binary accurate, because, well, according to my experience also with grid codes, one of the main problems is that in grid codes, when you compute the gravitational acceleration, if you spread the mass over a cell size, the accuracy of the gravitational force becomes much lower. And so it's fine for large scale distributions like stars in galaxies, but for point-like particles, it's a problem. And indeed, for instance, in Ramses, for sync particles and small scale simulations, they implemented a direct force summation.
Yeah, no, I remember this issue because when Romain was around, we were talking about that.
Yeah, exactly. So I think the point, well, this is what Paul told me when I was at KITPs, but maybe.
I agree that we should eventually go to, I mean, we could start to begin with a fixed orbit case so that we can also more similar to the KTP silicon binary in this case, but this is just you know, a default starting point, and then we have to go to live secondary. I completely agree. Especially because if you take, I mean, if you have some mass ratios that are at the boundary of where you could, also we had to decide the mass ratio to start with, but in cases where you are at the boundary between the gap opening and no gap opening stage, that's what Alessio, you were saying before, right? The live binary versus non-live binary can change the gap opening criteria.
Yeah, I mean, well, in general, what I believe is that maybe in the equal mass, sorry, in the equal mass binary regime, maybe it doesn't make too much of a difference evolving or not the binary orbit. But then in the planet-like regime, a planet that is embedded in the disk will accrete mass. And so, and I don't remember exactly, there is a paper by William Clay and Birch, I think. They compare both the live and fixed orbit planet, and they found some differences. So basically, moving or not the planet might change the structure of the gas around it. And I think this might be crucial for all the torque measurements. Although it also depends on the temperature of the disk. So the gap opening criteria also depends on the temperature of the disk locally, like around the planet. So it really depends on which kind of parameters we're thinking about.
No, that's right. And yeah, of course, we will target thin disks because that's more of the regime that we have in mind here in terms of H over R. Now, the other thing is 2D versus 3D, right? Because, I mean, for some codes, it's more natural to do directly 3D. I mean, for the particle codes, it's more natural to do 3D than 2D. But for the grid codes, usually it's the opposite, right? Or at least it's equally, equally feasible to do 2D and 3D. Now, the KTP one, I think it's basically using mostly 2D at the moment. Is that right?
Grid codes are running in 2D, and I think maybe somebody also tried with 3D, but mostly it's 2D, and particle codes are in 3D.
Yeah, no, I think all of them are in 2D. I think even Athena has been run in 2D.
Okay, but for example, the particle codes, like in your case, you're running 2D or 3D?
No, 3D.
You're running 3D. And
Yeah.
then how do you do the, in the analysis, how do you actually, so you will have to, so you take a slice to do the analysis, so to compare with what the 2D codes do, in terms of really how to plot things and how to do the analysis.
Mm-hmm.
What did you discuss between the different groups, how to compare the 2D and 3D runs?
Well, that wasn't really discussed. So there is an overlay with like the diagnostics that we are supposed to run, written for 2D. So in 3D, we had to come up with, like, for instance, for establishing what is the resolution that we have, we had to come up with like some strategies to calculate, to like convert like the smoothing length into an interparticle spacing, which is, almost the same thing that grid codes have. And that holds again for the diagnostics. So in terms of torque, then the computation of the gravitational torque is essentially the same. And for the eccentricity and the moments, then we basically translate all the equations into particles instead of grid. But yeah, we basically assume that we were like in 2D instead of 3D, which.
Okay, but you're using this, so when you do the analysis, are you using the same tool across all codes?
No. There are some tools that have been shared, but personally I haven't used them. So the only thing that we use that is common is Caitlin's routine to produce these binary files with the snapshots, so that there is a sigma for everybody, meaning the surface density.
You have the same. Okay, you have the same profile.
Yeah.
You're given a profile basically. Okay.
Mm-mm.
I'm going to share the screen now because I'm writing some little notes and then maybe everybody should see them. Okay.
I guess that's a good point. For example, the smoothing in 2D is not the same concept as smoothing in 3D.
Yes.
So it shouldn't, there should
One
be
has
some
to be
conversion.
careful with this type of things.
Yeah.
Yeah, that's also true.
Yeah. So I don't know. Do you see the share page?
I do.
Google? Yeah. So I'm writing, the things that we might start from. So, okay, the basic setup would be 2D, but 3D for particle codes again, because okay, I think in reality, even just with the fixed orbit and even the live case without sync, there is already some interesting comparison to do, because it's just interesting to see how the sinking rate or migration rate, or whatever you want to call it, how close it is between a set of codes, hopefully having SPH, grid-based hybrid methods like MFM and moving mesh like DISCO. So I think this already with the simple setup, I personally think it would be very interesting to see what comes up. And then one can go to the sync part, which is more tricky. So I would put the sync after one has done this part and the results have already been kind of compared, then one can go to redoing that or a subset of that, maybe just the live one with the sync. But this will be already a good set of results to look at.
Are they including syncs or sync comparison for the KITP
Good point.
project?
Did you hear?
No.
Yeah, there was an interruption of the audio. Sorry, Andrea, can you repeat, please?
Is there a comparison of sync prescriptions you've included in the KITP project?
I think there is, if I remember correctly. I'm just retrieving the overleaf, and there is at some point, I think, the idea to compare also difference in prescriptions.
I guess this could inform how we do this kind
Yes.
of analysis.
Yes, yeah, exactly. If they start before, then we can see if we have a similar, can use a similar approach. Yeah, so, okay, and let's see. I think this would be already, I would insist, whatever we decided in the different types of runs that we want to do. I mean, for the analysis, I personally would insist that we try to have the same tool if possible. I mean, there are tools that do that can analyze both particle and grid-based codes. I mean, I think in Agora, I mean, I lost track of what's happening now in Agora. Maybe Alessandro, you know better, but what is the tool that people are using at the moment to do the analysis?
YT.
It's still YT, okay. YT can do both, right? It's always been possible to do both, but since some time.
Yep.
I don't know if it can do, does it do, if you like for example, to measure torques with YT, is there something already built in, or would it be a routine that one has to add?
I'm not sure. I've never checked if such routine exists or not. I think it's not there because for galaxy formation simulations.
Yeah, because it's not a thing that people usually measure.
Yeah,
I guess it-
and since YT had been developed for ENSO and for cosmological simulations, originally.
Yeah, it's
Maybe
true that-
somebody implemented it, but I don't know.
Yeah, or one can also have, one can even write, if people like to do analysis in Python, one can even write a simple Python script that everybody uses to do it in the same way. For things like torques, it's not that complicated to do the analysis. So, yeah, I think it would be nice, even for simple things, it would be better to have the same analysis tool.
Yes.
Is YT set up for all different codes, or is it just something that reads HDF5 files generically?
It's set up for many different codes, mainly codes that are used for galaxy formation simulations. It has different interfaces, so Gadget, ENSO, Ramses, Art, I think Gasoline and Chang as well. And I don't remember now if there are others. Probably there are others, but
So that, I mean,
But some codes are missing.
yeah, some are missing.
yes.
But maybe it does also HDF5, because I mean, of course, that would be an advantage because most codes can do HDF5.
Yes.
And this could do it. Yeah. So that would be, no, this is something that we can see later, but I think it's just that we try to do it like this and then we see what tool to use. I think, of course, we need to know, as you said, Alessandro, we need to know how many groups and people could actually, take the burden to do this. And I mean, right now it's in these two rooms, the in-person and Zoom one, it's just a very small number of people. So really there has to be a follow-up that I commit to do, where I have to really find out how many groups would commit to have at least one person doing that. Because then we would have to have for each code a captain, and maybe two people even better, but at least one person that really has the lead of that code and the comparison. I guess it's the same thing that is happening at the KTP comparison at the moment, right?
Yes. Yes, there is one person in charge of each code.
Yeah. How many codes are now participating to the KTP one?
I think that's better.
roughly? I mean,
Let me, yeah, no, let me check. I can quickly look at the plot. So it's like, so it's 1, 2, 3, 4, 5, 6, 7, 8.
8 codes.
9 because there is the Jonathan's code that is missing, but 9 for sure.
Good number.
Which is probably a lot more than needed, I think, since most of them have the same basics and the same grid structure and.
Mhm. Yeah, and right. So, okay. I know of another code that are related people to the code that would definitely like to participate, and this is Frederic Massé and David Velasco. I mean, with the Fargo code, yeah, with Fargo 3D, and so they were interested also in the KTP one, but I think someone else is already running Fargo in the.
Yeah, Caitlin is.
Oh, okay. Yes, Caitlin herself. Okay.
But I mean, she's excising the cavity, so I don't know whether that is a requirement with Fargo 3D.
I don't know.
Also, it might work differently within the type 2 migration.
Mhm. So anyway, I mean, they are not participating now, but I know that they would be interested. And Frederic wrote to me again recently about that. So I think we can consider that part of this already in a way, which is good because Fargo is a bit different from both the other grid codes and of course also from the particle codes. So that would be okay. So you're saying 9 codes. Yeah, I think if we have at least 6 codes that have clear differences in implementation, that would be already, for me, that would be 5 or 6 codes to begin with. That would be already worth, in my view. I don't know what you guys think. Of course, 10 is better, but 5 or 6 where we have, let's say, an SPH code, a code like Gizmo, a code like Disco, and then Fargo, and then 2 codes that are like more static or refinement mesh finite volume could be Athena and Ramses. So if we had like these 6 codes, the SPH code could be either gadget or gasoline or chuck. So with 6 codes like that, it would be already very worth because you have 6 codes that are almost all of them have quite significant differences in the hydro implementation. And then it would be interesting to see the differences. As you said, if you have lots of codes, but some are very similar, it's not that interesting, or I mean, it's not necessary.
Yeah, I'm also happy to run Phantom if we want an SPH code.
Okay, so let's make, I mean, I'm just now making it up a bit because we don't know, some people will participate, but let's say a potential list of codes, let's call it like this. Potential list of codes. So, okay, so I put gasoline Changa because I mean we would do that. I mean, we mean myself and other people who run it. Then can I put down Gizmo also as?
Yeah, sure.
Then let's say also Phantom is okay, and then I guess Disco. I don't know if you, Andrea,
Yeah.
so we put down Disco. And then we have Fargo, which can do both the 2D and 3D. Then I put the names next to it, but this is more dynamic in a way. So okay, then it would be nice to have maybe Athena because it's also involved. It's also involved in the KTP one, and it's kind of the gold standard for finite volume static mesh. Then, of course, another finite volume code would be nice to have. For example, Ramses. I don't know who could do that for Ramses. I can't think of anyone who works on related stuff at the moment, but I mean, I could talk to Roman directly and see if he has some suggestions to do it. Because again, it doesn't have to be inside the working group already, or the consortium. Okay, so I mean, if we can already have this set of codes with people who are responsible for each of them, at least one for each of them, that would be already a good starting point for me.
Mhm.
And then, of course, it would be nice to have another, let's say, class eventual, another moving mesh code which is different from this code, like a repo. That would also be interesting. But no, yeah. Among SPH codes, I think if we have gasoline, Changa, and Phantom, I think it's already enough, because many of the other SPH codes that are around are either older in terms of implementation or very similar to one of these. So, I mean, for example, Gadget is older, implementation is older than either Changa or Phantom. So I wouldn't go for it unless there is someone that wants to insist to do it. But yeah. Yeah, so I think this would be already a good way to begin. And putting names next to, I mean, again, it's just tentative, so no worries, because we have to see how it develops. But for Castle in Shanghai, I can put down myself and Pedro. Pedro will kill me when I come back, but okay. So for Gizmo, I put down Alessia and Alessandro. I guess I put both your names, and then we. Is that okay?
Yeah.
Yeah, sure.
And for Phantom, I put you now, but then you find that there is someone else who wants to take over to avoid you being responsible for two. Probably it's better.
Okay.
I put a question mark here. Okay. So for Disco, I for now I put you, Andrea.
Yeah, sure.
Then Fargo, I put directly Frederic and then David. I don't know then who will actually do it, but I think Frederic also has another student who was interested. I can't remember his name, but I put this and then put the names just in case people don't know. Let's go. Okay, Athena, I wouldn't know specifically someone now who is doing the Athena one in the KTP comparison? Because one possibility would be to ask the same person if she or he is interested in participating to this as well. You know who is the one who's running Athena?
Alessia, do you know who is running?
Yeah, sorry. I was looking in the Slack. So there is Alex Dietman that is running it like as is, and Wang, who I personally don't know, who is running Athena excised, so without the cavity. But yeah, Alex Dietman is.
How do you spell it? Is Dietman?
Dittman. Yeah.
Okay.
Yeah, sorry, my voice is a bit low.
Okay, because maybe we can. I mean, we could contact him, given that he's already involved in the other one. Maybe.
Yeah.
Maybe he's keen on doing it. Okay. Then for Ramses, what I would do, I will contact Romain, and then maybe he will suggest someone. Okay, so this would be all right. And actually, I mean, I could. Yeah, I mean, if this really starts quickly and we have already these codes for a repo, I wouldn't know exactly. Is there someone for a repo in the code in the KTP code comparison?
Let me check. I don't think there is a repo.
They never participate.
Because maybe Diego was supposed to
Now
do
it's
it.
public.
So yeah.
Okay, I didn't know that. Okay. Okay, but of course, it's good to have someone who knows already a bit the code and is connected with, maybe not one-to-one, but at least somehow connected with the main authors. Yeah, okay, so well, I can also see if maybe I could also ask, I mean, I've seen that Volker now is getting interested in disks, so I can contact him to see maybe there is some student or someone who knows that might be interested in using it. I think also they actually no, I think Deborah Sijaki might be interested in this type of thing. And she's doing a lot of development in the code with her group. So, and she's also part of the, I mean, she's part of the astrophysics working group. I mean, she's
Yes.
not taking much the working group. Right, so we have to be a good thing. Okay. Okay, so this could be one initial list of potential codes and people. So for the setup, I mean, of course, one has to decide, okay, we start from a default setup with a given mass ratio and a given density profile and a given either fixed temperature or temperature profile, or but maybe on this, Andrea, you are more familiar with this setup, so maybe you can suggest.
For the Emory case?
Yeah, say very unequal mass binary or very.
Yeah, I mean, I guess it depends what the motivation is. If we're thinking about black holes and AGN disks, we can have some motivation for what type of aspect ratio you want to simulate, but then of course there's some numerical limitations. We can't simulate the most realistic aspect ratios, for example. So I guess we should just define some benchmark
Yeah.
value, right?
Yeah, we can.
Yeah.
We should also establish some like viscosity parameter,
Yeah. Yes, and
which also implies limitations for different codes.
that's right. So should we start from deciding what could be the initial default mass ratio that we would focus on at the beginning? Like, for example, KTP, I think they're focusing now, they're still focusing on one, right? Q equal one. Is that the really equal mass, right? For what I remember. And so here we could focus on, I don't know, something like 10 to the minus 2 or 10 to the minus 3.
Yeah, somewhere.
10 to the minus 3 maybe, because that's really a very different regime.
Yeah, you start to be in gap opening depending on the disk parameters, so.
You might, yeah,
That'd be interesting.
yeah, exactly, because maybe you'll see some slight changes in the codes.
Yeah, maybe it also depends on the physical motivation for what type of system we're trying to simulate. Like, if are we thinking of black hole binary mergers and what type of mass ratios we expect?
But I think,
That's a bit uncertain, I guess.
yeah, well, so I think one obvious thing is, first we would like to see, hopefully, if we can converge on the mean migration rate, right? And then we look at the fluctuations, right? Because that's the other interesting thing is the fluctuations of the torques. And
Yeah,
so, but first one would look at, I would look first at how much we can converge in terms of mean, the average value of the torque over time. And so the mean migration rate, basically. Maybe it works very well for all the cores in the same, and we go right away to look at something more detailed like fluctuations, but we don't know. It's not obvious. So in your experience, if you choose 10 to the minus, yeah, you are in this regime that would be like a borderline between the type 1 and the gap opening phase, depending on these parameters. So maybe we should choose something smaller to begin with.
Yeah, in my experience also, it's beyond above 10 to minus 3 where you start having torque fluctuations, at least in disco. There's some
It's
strong-
above 10 to the minus 3
At 10 to the minus 3.
or bigger.
Yeah, and as you increase
The
the
mass.
mass ratio, then there's just more gas piling up around the secondary, so there's more,
More
you really need to resolve that more. So it's more
So that in that sense is more, yes, it's more tricky, but also more interesting.
Yes.
But maybe for aligning the codes, probably would be good to start from a case that we expect to be very clean.
Yeah, but like 10 minus 4.
Yeah. I think so. I mean, maybe because this way, I mean, that's a case where we should easily align the codes. Then we can go to 10 to the minus 3 and or higher and see.
Yeah, that's a good point. Yeah.
Maybe. Yeah. So maybe start with, say, Q 10 to the minus 4. Later. And then the disk model. So the disk model. So the profile that we have to choose is. What do we choose?
So a lot of people will do a constant density profile, for example, just to keep it really simple. But I think a profile, some profile decreasing with radius is more physically motivated. And
Yes, no, I totally agree with you on that.
So in the cavity case, so you chose a surface density profile based on default choices of previous work, or what was the?
So there was this flat surface density profile. It was like just like a constant and then some tapering at the inner and outer edge. Just to, I think it was somehow converge on based on the fact that we in particle codes have a finite mass disk, while for instance disco has a constant and dot at the outer edge. And so that gives a steady state disk. And I don't know, maybe it was, so the flat surface density profile was better for both, even though it's highly unlikely that it's gonna be something physically, real.
yeah, I guess it just makes the boundary conditions easier.
But for example, in the ones that you published with this, what profile did you?
I had a profile.
You did it,
yeah. Like r to the minus 1/2 or something like
So
that.
some power law.
Yeah, because for those ones, we wanted a constant aspect ratio,
Mhm.
right? So there's a connection between the two. So you have to choose what you want to constrain, and it will imply something for the rest.
Mhm.
Right.
Yeah.
Yeah, another possibility would be, sorry, go ahead.
Oh, I was just gonna say, if it's a stationary simulation, holding the black hole fixed, then maybe this makes it simpler. I mean, we don't have to think so much about the profile. And I mean, it definitely will make a difference for the torque, but.
Yeah.
What you were saying, Alessia?
No, I was saying that maybe we can, so I think in the planet community, they usually use like a power law, but then there is some tapering. So we might want to, look into that. I don't remember exactly how is the profile, but maybe we can assume some profile that is similar.
You're right. I mean, actually, even in this Fletcher et al. Code comparison, we did something like that. I don't remember now what profile we used, but it was a power law with the tapering. So I can look at that and also at other examples from the past in the planet case. Yeah, that's a good point. So define just like define a power law density profile. Okay, yeah, so we'll find some slope that we like with tapering. Okay. So what else do we have to for density? Well, the temperature.
Another very important aspect is whether we want to. So, okay, my personal opinion is that we should all do at least alpha disks. but I know that many simulations do new constant.
Okay.
So if it's I don't think it's an issue either ways, because it should always be possible both in. So for us, it was possible to just change it to new constant for the code comparison. So I think that even in grid codes, it should be fairly straightforward to just, yeah, I see Andrea is nodding. So yeah, it should be straightforward to do alpha disks.
I mean, I would definitely, I didn't realize that. So in my mind, it is an alpha disk that people should do. But so you're saying that some codes also in the comparison, they do new constant.
We all do new constant in the code comparison. The issue with that is that if you infer from your constant new the equivalent alpha value that you should have, it's above 1 for h over r of 0.1, for instance, which is the value, the temperatures that we are assuming, then the alpha parameter is above 1. So it's outside, it's like almost 2. So
Yes,
it's
yes, so
outside
it's-
the fiducial range, let's say.
I mean, so it's done like that because it's easier for some of the codes to do that. I would have.
No, I don't think it's easier. I think it's just because it should be, as I said, pretty straightforward to implement both versions. I honestly don't know why we're assuming constant new, probably because, so I mean, so there was a recent paper by Alex Dietman that investigated so constant new basically allows you to investigate separately the effect of the disk of alpha and of h over r, versus if you do an alpha disk, then they are both in the same equation, and so if you change one, then you change the viscosity, like regardless of what the other parameter is.
You know what? One thing that, I mean, maybe in the circumbinary in this case, this is not actually, it's not an issue in the circumbinary in this case. But what I'm going to say now, so the comparison with literature that is most abundant, that's from the plan migration case, it becomes impossible because in that case, you know, it's always been an alpha disk as far as I know. So
yeah,
look at the effect of alpha all the time or they kept alpha fixed. Or either they
I
vary
thought
or
there
they,
was a lot of cases with new viscosity for planet simulations. Maybe I'm just thinking of, I know Paul has done this, but he's also
Yeah.
cited some more for comparison.
maybe the code comparison, but I mean, as far as I know, you know, there have been papers that have looked at the effect of viscosity, meaning if you change alpha, what is the effect on type 1 or type 2? For example, for type 2, that's usually what people do, right? They change alpha and see whether you move the gap opening condition, basically, by changing alpha.
Yeah, but I think it
Right.
depends on how your torque is sensitive to viscosity at the radius it's at, right? Because I think some of the predictions in the planet migration case for type 1, whether or not the co-rotation torque is saturated or not,
Yeah.
those predictions are done or given with a new viscosity. And then if you have a new viscosity, you effectively have an alpha varying with radius. So-
Okay, maybe you're right. I mean, mine is again more the transition type 1, type 2 that is really measured with alpha. But
I agree that alpha is more
yeah.
intuitive to me.
I think what Alex Dietman's paper also shows is that if your this aspect ratio is below 0.1, then doing an alpha disk and doing a new disk gives you very different torques.
Interesting.
okay, which is our case will be much less than 0.1, right? We have to do something less than 0.1.
Right. Yeah, I know that's the other part that we need to discuss, like what kind of aspect ratio do we want to consider?
Yeah. So very small, of course, it's more difficult computationally
Mm-hmm.
because you need to.
I would say at least below 0.1.
Mhm.
And yeah.
So I don't know, we could try 0.01 as a default case.
Yes.
Or 0.05.
Yeah.
0.01 is, I think it's I don't know, for at least for SPH and MFM, it's very feasible.
Yeah, I guess for some of the other codes, you'd have to find a way to measure if you're getting some kind of accumulation of error from having 0.01, because that's quite supersonic.
Yeah,
Most of the work that exists uses 0.1, right? So it's kind of nice to compare to, but also not realistic.
let's
Right.
say, I put a range for now, and then let's say it has to be somewhere between 0.01 and 0.0. We don't want it larger than 0.05. We could go to 0.01, and it would be better. But okay, this might be discussed a bit more fine tuning when we have all the people committed to do this.
Yeah, I just like, for example, I think, like David and I were already comparing some Disco and Fargo 3D simulations recently, and we found agreement with H of R of 0.1 and then disagreement with H of R of 0.05, I think it was, I have to check. So it just showed, if you wanted to converge your results earlier, and then explore, it might be better to start with a less realistic case, but then I think it will be more
So
interesting.
that's a good point. Yeah, so the better, yeah. So for the initial alignment phase, we want this initial alignment phase, right? So, okay, let's see. Otherwise it's not practical.
Yeah.
Okay. Some choices. Maybe I realized, just have to remember what we need. Okay. But maybe.
Because I think I would start to expect more differences when you decrease the aspect ratio. So, yeah.
Yeah, so this could be a bit like the mass ratio, that we start with a case that should be clean, numerically clean. And then we move to the cases that are probably more sensitive to the numerical implementation.
Probably one thing that it's worth keeping in mind is that the value of H over R at the planet location, or at the secondary location, it determines the gap size and gap opening. So we want to, to think about that. Like if we want a gap or we don't.
Yes, I mean, if we take, but this in a way we could actually handle by choosing that in an initial model, a Q that is small enough, like, I mean, 10 to the minus 4, but maybe even small. 12, I would try to avoid it in the first set of run.
Okay. That makes sense.
Because it's easier to, it's a cleaner convergence test, right? You should mean that the type 1 regime is basically linear torques, right? So it should be the easiest to converge.
Okay.
So, and then of course we have to go also to the gap opening regime. So eventually we'll have to raise Q or change H over R. That's see how to do it better.
Yeah, might have to make a pretty small Q with H of R.
Yes, we either do, right. Of course we have to balance that. Yeah, we have to decide. I guess, if people are fine with doing 0.01, then we adjust Q accordingly, right? Meaning, if you have 0.01, maybe Q 10 to the minus 4 is already good, or do we have to go to even lower in order to not open again?
I think there would be a partial,
So maybe we have to go
I'm
to.
not sure, I haven't checked,
But so we could first agree on the H over R, because that seems more numerically tricky for some of the codes. And then once we agree on that, we adjust the Q in the default model. Then we can change it, of course, but in the default model, we adjust the Q to a value that for that H over R should not open the gap. Right? That's, I think, what we could do. Let's say, eventually adjust Q. Just Q in the initial model. Once H decided, we want to avoid gap opening. First set of,
I guess we would have to check with the experts of some of these other codes, but I think there's a reason why most simulations don't run with H over R 0.01 for the grid codes. I don't know if it'll be a challenge necessarily for some codes to run it at all.
Yeah, no, I mean, if that turns out to be the case, then at least to begin with, we have to start with a larger value. Yeah. Yeah, no, I agree that after talking to the respective people, then it should be clear. Yeah, so okay, what else? I mean, for the initial case, for the simple, vanilla case, we do, well, we should do, I think we should do from the beginning both isothermal and adiabatic, right?
Yes. That so yeah. So the other point would be in the case of isothermal, then how HRR changes if we want it to change, or we just want it to be constant.
Yeah. You mean change it in different runs, or?
Well, in the isothermal, just change it with the radius. No, I mean, we're gonna assume locally isothermal, right?
Yes, sorry,
Yeah.
right, local isothermal. And then there is the viscosity. That's also another decision the one has to make. So should we viscosity? Choose alpha or no? Possibly, I would say possibly constant alpha to begin with. And I mean, let's say we choose alpha as the reference parameter. We could start with, again, a value that is quite common. Let's say 10 to the minus 2 or 10 to the minus 3, somewhere between 10 to the minus 3 and 10 to the minus 2. It's quite commonly used also in planet migration. 10 to the minus
I think 10 to the minus 3 is not terribly feasible in SPH.
10 to the minus 2, maybe, right?
And also,
That's used for some of the simulations.
So sorry, Alessia, we interrupted you. You were saying?
no, that's fine. No, I was just saying that point like 10 to the minus 3 might be challenging for particle codes. 10 to the minus 2 is fine, but I think even 10 to the minus 1 is not, it's okay. Like for AGN disks, you would expect alpha to be
No, you're right, because you have an alpha. Yeah, no, sorry.
larger.
Biased by the protoplanetary, so you're right. It's more likely.
Yeah, in the protoplanetary case, then it's gonna be way lower than that.
I think my understanding is that the MHD simulations for AGNs would predict alpha around 0.01, but then observationally we have some constraints that would suggest it to be higher.
Yeah.
Yeah, no, I agree. Yeah.
Okay, actually, that makes it easier to avoid the gap opening, right? Because it's harder to open a gap with larger viscosity. So,
Yes.
I mean, the philosophy of not having a opening at the beginning, that's okay. I mean, it's not harming. Okay. I mean, these are basically the choices that one has to make. I can't think of any other major for this first set of runs. I mean,
Well, some common resolution.
yes, then we
defined
have,
by, like,
yeah,
I don't know how you'd compare it between SPH and grid code.
yes. No, then there are the numerical, yes, let's say, let's call them, this is, yeah, this was like the model setup. Now we have numerical choices. Okay, resolution. And if we don't do the sync initially, we have still to the softening of secondary black hole. So these are the two things.
Domain size.
Domain size, you mean, so the size of the boundary of the disk.
Yeah.
Disk boundary, yes. Well, again, here is where it gets tricky because, of course, the particle codes can do void conditions or no boundary condition, but the grid codes would have always to do something about that. I don't know what you do in this code. This end dot thing that Alexia was saying.
Yeah,
right?
usually.
It's a inflow boundary condition.
Yeah.
Yeah, these are the things that are inevitably going to be different, but that's okay. That's part of the comparison. Disk boundary. So what, I mean, how to, are you discussing this thing about the boundary conditions, how to keep in mind the boundary conditions being different in the codes within the KTP code comparison?
I don't think that has been discussed really.
Because I mean, to a minimum, it would be good. So what we tried to do long ago for another disk comparison, where we had grid and SPH codes, because we couldn't align everything, of course, in the boundary stuff, we decided at least that grid codes should try to have the same boundary condition or something very close. And of course, the SPH would have just void boundaries, but at least the grid codes would try to do the same thing. And
Mhm.
that would be, that would be desirable, but I know that there are different implementations, so I'm not sure that can be done. Let's say, but at least there should be a discussion of that. Once we have everybody on board, possibly align grid codes. So, Alessandro, can you remind me, in the Agora, when we did the isolated disk, the
Yes.
paper, there was one. In that case, I can't remember what was done. I mean, in the grid codes, what was done for the boundary condition? Was it the same choice of boundary condition or?
Yes, I think the box for the grid codes was in outflowing boundary conditions, and of course for particle codes, when you don't set anything, it's flowing anyway. Particles will always stay there. The only difference was that in grid codes, they had a low density hot halo, gaseous halo, because of course you always need a minimum density in the box. While in the particle codes, we didn't have gas mass outside the disk at the beginning.
Yes.
So,
Yeah, that's right. That's usually a difference. That, I mean, it's an inevitable difference that you have every time you do the.
well, we could have tried to include a gaseous halo also in particle codes. It would have been feasible,
Yeah.
but well, after 2 years trying to get something out, you accept what you get.
Yeah,
And in any case, it didn't play any significant role in the evolution. Of course, there were some small differences, especially in the outskirts of the galaxies. But apart from that, most of the properties were consistent. So.
Okay, well, I basically wrote that we should try to align them between grid codes, but it's open for discussion when we will have the other codes, but in the discussion. Okay, so then, well, of course, resolution. Yeah, so that's the usual thing about comparing the particle and grid-based resolution.
Yes.
It's always a bit tricky and a bit subjective, depending on what criteria people want to use. But for example, in the DISCO runs, the published ones, the resolution that was considered like default was which one?
I forgot what it was exactly in terms
It
of
was
how many cells in the smoothing radius, for example. That was one thing we would check, and there was like 20 or so cells across the smoothing radius.
That's you mean the smoothing of the black hole?
Yes.
But the grid resolution.
I mean, I know like how many cells, but
Yeah.
it was like 500.
the desired. Okay. The desired resolution in terms of interparticle spacing was 0.02 A.
What did you say?
Sorry, the desired resolution that we set for the code comparison KITP was 0.02 A at R equals 3.
A is the separation.
Yes, it's 0.02.
Yeah, at R equal 3.
Yes,
Okay.
that's right.
Where in the just from the KTP, where the disk radius was the total size was
The total size was 2 to 10.
Okay, I see.
That's a nice way to define it.
It's adimensional, that's good. Okay, well,
I guess it will vary, like with Disco and some other codes, you can have like a logarithmic grid, for example, or you can define a different number of cells as a usually, that's different between Fargo 3D and
Yes,
Disco, for example.
yes, that's where, yeah. Yeah, so this is where it gets, I think what one could do, that's the same thing that we had, the same problem that we had long ago with this other Discord comparison, is maybe to say, okay, let's define a resolution which is a reference case for a very simple setup, like if you have, fixed Cartesian grid, for example, or you choose one, it could be fixed Cartesian or fixed polar. Then, you define the resolution there, then the other codes that have more complicated grid structure can try to have a resolution that has, I don't know, 50% of the disk resolved at a similar resolution, or something that they use as a calibration. This could be one way, to at least have a reference, because if you tell people just do whatever you want, it's out of control from the beginning.
But couldn't you also just say we want the results to be converged? I mean, if you change resolution and your torques change, that's not good, right? I would expect on average your torque should be the same with higher resolution. So as long as your result converges.
Yes, but you might have, eventually, yes, but you don't know how fast each code will converge, right? So you don't know, there might be codes that need many more iterations in resolution to converge than other codes. I mean, this is part of what we have to find out. You could do it like that, but you don't know how fast you get to converge. I think it's still, I mean, I know it's not an easy exercise, but it would be good to have at least some simple calibration of the resolution. Then each code will be slightly different because the grid structure is different and the particle mapping into grid is not trivial. But I mean, something that at least is for example, between SPH or particle methods and grid based, you can do something like so it's really we did with lumping and trying to remember, because the trivial thing that people do, but it's not the right thing, is to say, I take the smoothing length equal to the grid cell size. So the smoothing length in SPH or in a code like MFM, to make it equal to the grid cell size. But this is not a good thing because the particle codes use mass as a resolution criteria rather than size. So it's not really the same. I mean, Alessandro, remember you were looking into this too at some point, right? This how to map the two resolutions.
Well, I think for galaxy scale simulation, it's easier because usually you have the softening length and you can compare that to the cell size in a grid code, because what you care the most is gravitational force resolution. For these kind of simulations, if you don't have self-gravity, then of course gravitational softening is useless.
Yes,
for the KTP comparison, what at least Alessia and Enrico agreed upon is to use the interparticle separation.
Okay, so interparticle separation. Okay, interparticle separation. So that means that if you have a okay, so that's stricter than kernel size, basically, right? So you have it's like a
Usually, it's a fraction of the kernel size. Then it depends on your kernel. But for instance, a cubic spline with 32 neighbors is about well, if you assume that the kernel extends to 2 times the smoothing length, the interparticle separation is on average the smoothing length.
That's right. Yeah. Yeah.
If you increase the number of neighbors, it varies a bit, but in the end,
but then,
more or less.
Yeah, but then when you compare with the grid case, what you say, you compare the interparticle separation with grid cell size, or
yes, this is what we're doing for the KTP comparison.
okay.
Of course, it's not an exact comparison because the intrinsic nature of the code is completely different, but it's to give an idea of what is more or less there.
Yes, because when, I think I have to go back to this, but I remember that when we did, you know, this paper with Omping on the MRI with MFM and Athena and SPH,
Mhm.
and when we compared with Athena, there was this tricky thing that if we were using a criterion like this one, the results were very different. But then if we were comparing by saying, we have, so what we were doing, so we were trying to get some way of converting the mass resolution into volume for the grid code. Mass resolution in MFM or in SPH into volume. And so basically by doing that, then we had to compare with a MFM simulation that was much higher resolution than what we thought initially with just the interparticle separation. And then when we did that, the comparison with Athena turned out much better. I have to go back to the paper exactly how much was the effect. And I remember that this got much better once we used the stricter criteria, which effectively was making the resolution requirement much stronger for the particle codes to match what the team was doing. And yeah, so I guess we can think about this, but this is possibly a starting point, interparticle versus grid size. Okay. The softening is, yeah, we should try, well, I guess depends on the implementation of softening. Let's say close similar scale lengths, but we will see.
Mhm.
And then I think there are, I mean, I don't think there are there other major things that one has to decide in this first phase?
I guess there would be differences in output, but that's a different
Type of thing, yeah.
type of thing.
Yeah, so
Frequently you
yeah.
output data and stuff like that.
Yeah, so. Yeah, input, output format. Output structure and format, both of them.
For example, for calculating torques, you could, calculate it during the simulation and calculate the torque exerted by different regions, for example. So you can focus on gas like close to the black hole or from the cold
Yeah.
disk.
It's for the analysis, you mean?
And that, yeah, but that could be done, if you could do it in analysis, post-processing, or you could do it, in the simulation and output it. Sometimes that's easier, but I
Okay,
guess that depends.
yeah, that I think in general, to make it easy for most codes, it's probably good to do it in post-processing.
Yeah, I guess it's for the live case where
Yeah.
you would probably want to do it during, but I don't have experience with that.
Mhm. Yeah, okay, but we have to keep that in mind. It's certainly, analysis on the fly versus post.
I mean, it depends on how frequently you want to measure the torque, because you don't want to output a checkpoint
Yeah,
every orbit to calculate a torque for every orbit. But if you only want it every
yeah,
100 orbits or so.
Yeah.
it's easier.
yeah. Okay. And then, of course, someone will have to, I mean, like you have been doing for the KTP case, someone will have to produce a template initial condition, right? So, or even just provide a profile, and once we decide which one, this is more like programmatic. Someone has to be responsible for placing somewhere the profile and the data that people need to have from the beginning. Let's say there must be a initial condition capture. Let's call it
Mhm.
that. Okay. Yeah, so I think we have already quite a few things. I don't know how much further we can go before knowing who would commit among the non-present people. Yeah, any other comments? Because I think the next steps for me would be with this draft of a structure that we put together now, I would, well, first remind the whole working group, sending a link to this Google Doc so they can see that we have done some practice, some concrete discussion about it. Maybe that, you know, more people get motivated. And then if nothing happens on a short time scale, I will reach out specifically to people who might be involved. I mean, some of them that we listed already, who might be involved in each of the codes. I mean, someone like Roman I could contact already because he's not in the working group, he's not in the LISA consortium, but you know, I could offline tell him about that. So I guess my first action item would be to send an email out to the whole working group with the link to this Google Doc and asking for comments, and also, you know, I will leave the list of the codes on. So I would say that this is just a preliminary list, and the people who are assigned are just the people who already participated in the discussion and volunteer, but it doesn't exclude that other people can be on board even on the same codes. Actually, we would like other people to be on board on the same codes. And then anyone else who has another code that is not here and wants to participate, they're super welcome to do it. So it will be inclusive as much as possible. But of course, you know, once someone says I want to do it, there are commitments. This is more a discussion that's true for all the projects. And then there has to be some commitment. And I guess for that, we need to have another meeting. You know, once we have a list of 10, 15 people that are.
Yeah, I guess it's good to point out, like it was already said before, that even if you're not running the simulation directly or don't have experience with one code or another, there can still be a lot of analysis or things to do in other ways. So
yeah, participation. Analysis.
Yeah.
Other work, other useful work. Useful work. That is not directly the simulations. Okay, yeah. Okay,
that's good.
yeah, I think we went as far as possible for.
Yeah. I guess you just get people interested and then schedule a telecon with everyone at that point.
Yeah, exactly. So the idea is first the email, hopefully some feedback will follow, I hope. People will get this link so they can also add directly comments or put their name. I will explicitly ask to put their name if they want already in the Google Doc, and then we will have to set up a new Zoom call. Possibly not too far in time, maybe by the end of July, or not before the end of the summer, not after the end of the summer. Otherwise, it takes too diluted in time.
Sounds good.
Okay.
If I can make a suggestion.
Yes.
Regarding what you
No,
just
go
said,
ahead.
you know, regarding, you know, adding comments in
Yes.
the Google Doc.
Yeah.
Especially for this last bullet regarding
Your participation.
contributing
Yeah.
without being capable of running the
Yeah.
actual code.
Yeah.
Having a few examples of venues where it might be useful is going to
Yes.
be definitely something encouraging other people to
Yeah.
collaborate.
Okay.
Like providing a small example of at least the type of analysis that you can run or the type of post-processing. I don't know, I'm just trying to
Absolutely,
figure it
yeah.
out. So maybe suggesting and encouraging people to add in
Yes.
comments there. So
Yeah, and analysis means, of course, you know, practically doing it, but also if one has tools that can be useful, that also is.
Yeah, I guess like, for example, if we want some common tools to compare torques, for example, I mean, there could be definitely a way to contribute there by comparing the way torques are calculated in different ways, or seeing what the packages in YT do, for example, for different codes. I'm brainstorming.
Yes, yeah, exactly. Let's say so. Let's see, looking at codes.
There's definitely a lot more. I just need a coffee.
Yeah, we all need it.
Yeah.
almost there.
Analysis that can interface with many codes.
Also comparing, I mean, there's always the usual aspect of, gathering literature that's relevant. I mean, we should all
Yeah.
be doing that, but like personally, I need to review some of the code comparisons you talked about yesterday. I have to check the planet ones, for example.
Yes. Yeah, absolutely. I'm writing down all these things. Cutting liters is useful. Yeah, comparisons and beyond, because it's not only the comparisons.
And beyond, yeah.
Mhm. Yeah. I think
That's
there
already
is.
open stuff, but yeah, I'm sure there's more things that will just naturally arise.
Yeah. Yeah. Okay. Then I guess, yeah, we will continue through email and then a Zoom call, possibly not too far in time.
Just one thing, Lucio. This
Yeah,
concerns
right.
the binary. So
Yeah.
are we saying that we will only do that, or
What do you mean? Sorry, I didn't catch the
there
last.
is the large scale, the other project?
Oh, yes, yes, right. So I think, that things happen naturally sometimes. So the way I would put it is, we have produced this document now, which, because we thought it was easier, is focusing on option one, right? We are not
Yeah.
excluding option. So I mean, in the email, I think I know what you have in mind. In the email, I can still say that, option two is not excluded, that, it's not forcefully
Yeah.
not happening. But we have already drafted this plan for option one. And so I think we should continue with pushing this at this point, right? Because
No, I totally agree. I was just saying that since there were two options at the beginning, we should
remind people that still exists. And if suddenly there are 10 people who say, oh no, we want to do that, I will commit, we take responsibility, why not? No, absolutely.
Yeah.
But knowing how people tend to be, all of us, tend to be sometimes too overwhelmed, when there is something already there, it's easier to attach to that, right?
Yeah.
So, okay. Well, thanks a lot for all the help and suggestions and feedback. And yeah, so we'll take it from there.
Looking forward to some
Thank you.
comparison.
Yes. Talk to you soon, all.
Okay, thank you.
Bye.
Bye.
I
Now we have time for a break.
Yes. Yeah. It doesn't hurt to break a bit.
Yeah, it's just a lot of
Okay.
using my brain
Yeah.
today.
Yes. Okay.
Yeah, I guess I'm curious who else is in this KITP comparison.
So
I think a lot of the people could then contribute to this one, and it wouldn't be much difference if they just change some parameters.
yeah. Last week when I was in Munich, I met someone who is actually involved since not the beginning, but more like lately. Actually, she uses another code that would be nice to add. She uses Pluto.
Oh, yeah.
Anna Pensley. So she does circumbinary disks in a planetary case. So circumbinary planets.
Yeah, I just saw her paper through because
Yeah.
of Chris's talk today. I saw the reference and I
Yes,
was like,
yes.
oh, I didn't see this one.
No, exactly. And yeah, so she uses Pluto. And we were talking about not only the code comparison. I think I mentioned to her that we were going to possibly start other code comparisons in this group, in the LISA consortium. And yeah, so she was also interested to not just stay in the planets and we also do something else. So maybe that's another person I could contact.
Mhm.
And she seemed very, very motivated and she understands Pluto very well. She's done her PhD work with Pluto. So,
That's great, yeah.
so actually, let me add them. I forgot also, let's see, Pluto.
suppose someone could well just learn how to use the new code if we wanted to include it, if there's good enough
Yeah.
documentation.
Yes, but
It's less ideal, but
if there is a good motivation, like a technique that is different and, we really work.
yeah. But that's why I was surprised if Alex Dittman is doing, was it Athena, or his last paper was with Disco, but I think he's just very proficient in just learning a new code and then.
But even I know that is well documented. Everybody tells me that it's extremely well documented. But still, when you use it, for example, Omping did use it himself. But then when we had to do this comparison of the resolution and so on, then it was much better to involve. In fact, we involved Shunin Bai, who has done the thesis with Pluto and with Athena as one of the main experts of Athena. So he ended up in the paper, but it was a good thing because it saved us a lot of time and maybe also mistakes in doing the comparison. So
Yeah, that makes sense.
yeah. But yes, if someone wants to learn another code, why not?
Yeah.
Okay. Also, because we have another discussion. So you have to share the other one.
Yes. That's great. I love chairing, but I don't know how many discussion points are already posed on the
tablet.
tablet. I don't check.
So actually, I have to write to the other two co-chairs. Valeria is already too busy, so I won't write. But the other three, including me, we have to be in one of the. Each of us will be in one. I think I will be in the Emirates because Marta will be in the massive black holes, and I guess Shane will be in the stellar binaries with Valeria. Probably. Let me check with Shane because I think he might be also interested in the Emirates.
Because he did post a question.
Yes, so let me
in
actually
the Emirates one,
check
so-
with him because maybe he wants to be there.
Yeah. I'm interested in the black hole binaries discussion as well.
Yeah, I said I'd like to be both.
How do you join the LISA consortium Slack?
I
did it a lot of time ago, so I don't remember.
actually think that if you have a username, I probably can invite you.
Yeah, because I guess I just couldn't find an invite link like in my email, and I think if I just try and go to it, I don't think I can just join it, right? What is it called? LISA consortium?
Yeah, it's a consortium is the main channel, and then there are all the sub-channels, like the one for the meeting.
Okay, so I think I would need an invite link, right? I guess it.
I should know, but I don't.
You found it.
Yeah, I don't know how to sign into Slack, even though I use.
What's your email?
Thank you.
I think it should work, but I'm not sure.
Oh, this is a different kind of keyboard. Where's the at?
Yeah, it's Italian one, sorry. What do you need?
The email at sign. Oh, right there.
Okay.
Thank you.
Yes. You should receive the email.
I might be traveling in the air. Oh, nice. Thank you.
many channels. I guess we're still in Zoom. I don't know if we're supposed to stay
Oh,
connected.
Yeah, I was waiting for the end of the hour just to close
All
it
right.
at the scheduled time, but it's, I mean,
Yeah.
I guess we can close it now. It's just gonna make the recording shorter.